Hello and welcome to the first in a series of webinars that are being presented by the Electricity Sector Climate Information, or ESCI project. The ESCI project is, sorry. Sorry, I think I muted myself. And it's undertaken by the CSIRO and the Bureau of Meteorology in conjunction with the Australian Energy Market Operator. My name is Rebecca Gregory and I'm the CSIRO project manager for this project. Before we get started, I just needed to mention a few housekeeping items. As you can see, you've all been muted and have videos turned off. This is just to reduce the feedback and distractions for the presenter given the large number of participants. But please use the chat function on the Zoom toolbar to ask questions throughout the webinar, and these will be answered by the presenter during a Q&A session at the end of the presentation. We'll address as many as possible. Today's webinar is entitled Modelling the Future Climate, and it's being presented by John Clark from CSIRO. John's the research team leader of the regional projections team at CSIRO and leads the communications and stakeholder co-design component of the ESCI project. He has around a decade of experience developing and delivering tailored climate projections. He's currently leading the upgrade of the Climate Change in Australia website, where the data created by the ESCI project will be hosted. So on that note, I'll hand over to John to start the presentation.
Thanks very much, Beck, and welcome everybody. Thanks for joining us. Yeah, we've still got people joining us, but that's okay, we'll make a start. All right, so today's the first webinar in the webinar series for the ESCI project. And as Beck mentioned, there are a number of collaborators. You can see on the title slide there, Bureau of Meteorology, CSIRO, and AEMO, along with the Commonwealth Government. But firstly, some background. So we're going to be looking at how we go about modelling future climate. But firstly, why? Why are we even doing this project? Essentially, in 2016, the Finkel review made some recommendations around preparedness of the electricity market for future climate. And so that was really, it was those recommendations that led to this project. Just a minute, something's going wrong with my slides. That's better. All right, apologies for that. And sorry, just lost my flow. So we know the sector is vulnerable to climate. It's been known for a long time. For example, in January 2009, there was an extreme heat event, particularly in southeastern Australia, that resulted in multiple line failures. The Basslink connector was shut down and 500,000 residents in Victoria lost power. So one of the questions that was asked subsequently was, will this happen again and will it be worse? Hence the ESCI project. Sorry for the pause. I've just got a problem with my display. It's not showing me the right slide. It's okay. Just move things around a bit so that I can see the other screen. All right, so the project is about looking at the risk that's posed by climate to the electricity sector. And so what is climate risk? So we can look at the definition that's been developed for the National Disaster Risk Reduction Framework a couple of years ago. Climate risk refers to how climate change could impact social, economic and natural environments. And it's made up of two primary types, physical risk and transitional risk. And they also give rise to secondary risks, including liability. And consistent with the IPCC's report in 2012, a combination of hazards and exposure and vulnerability is what constitutes a risk. That's fairly standard risk definition. Within the electricity market, sorry, still having problems with these slides. Within the electricity system, the sector has identified 5 main vulnerabilities. And these are around heat, bushfires, wind gusts and cyclonic storms, reduced dam inflows and flooding, and coastal inundation. Now, the ESCI project is going to be addressing the first 4 of those, but not the coastal inundation work. So what I'm going to move on to now is how we go about developing climate change projections. So we start with observations and our understanding of the climate system. Knowledge of how the climate system functions has been around for a very long time. It's a very well understood system, and when we're talking about observations, we're talking about observations from around the world. Armed with that knowledge and those observations, we can look at future scenarios, and specifically for climate change, we're interested in future scenarios of greenhouse gas emissions and aerosol emissions. We can use those 2 tranches of information in combination to inform the development and the running of global climate models. And by running multiple global climate models, we can end up with some climate change projections. That's the fundamental approach. The climate system is a complex thing, and this diagram attempts to illustrate most of the features that you can find in a global climate model. So essentially everything that happens in the atmosphere, everything that happens in the ocean, a lot of the processes that take place on land, and the interactions between those all have to be taken into account, along with what's going on in the poles. And you'll see the word coupling quite a bit there on that diagram. This relates to the communication of information between the different sectors. So the atmosphere is one part of the model that is coupled to an ocean model, so they talk to each other and exchange energy in the model. As I mentioned, the understanding of the climate system has been around for quite a long time, and the processes can largely be expressed mathematically. Luckily for us, once you can express something mathematically, you can use computers to solve equations and help you get the answers that you might otherwise not be able to solve in your entire lifetime. But in order to inform these climate models, we need to know about the future scenarios of greenhouse gases. So the international community, coordinated through the Intergovernmental Panel on Climate Change, reach agreement on what those scenarios of greenhouse gas and aerosols look like into the future, so that all of the research groups around the world, and there are quite a few who develop climate models, this is to ensure that they're all using a consistent set of scenarios so that their results are all directly comparable. So what this plot on the left of the screen shows is lines that represent essentially 4 main future emission scenarios. So you can see that this goes from 2000 out to 2100, so essentially the 21st century. And you can see that there are several lines showing the progression of emissions in gigatons of carbon through time throughout the 21st century. And this second plot shows the concentrations of those carbon dioxide gases in the atmosphere at those same points of time. So there's a correspondence between, say, this blue line in the left plot, which represents this RCP 8.5 concentration pathway, and this blue line in the right-hand plot shows what that will result in terms of well-mixed carbon dioxide in the atmosphere. The reason it's not the same shape is that there's a lag from when carbon dioxide gets emitted at the Earth's surface and makes its way up into the atmosphere. It takes time for that to become mixed evenly throughout the atmosphere around the entire planet. And so there's a time lag. There's also a range of processes that go on, which you can see illustrated in the earlier diagram, really. When carbon dioxide makes its way into the atmosphere, let's say from an industrial emission, so it's taken out of the system as far as the atmosphere is concerned. But of course it does things in the ocean, like changes the chemistry that's going on in the ocean and makes the ocean less alkaline. So fundamentally, there are these 4 representative concentration pathways, or RCPs, that are used for modelling future climate, and these allow us to explore different possibilities into the future. Of course, we don't know which of these we will end up following. We probably won't follow any of them. We'll probably follow somewhere in between. But up until the present time, we've been more or less following the RCP 8.5 pathway. More recently, there's a suggestion that perhaps we're dipping below that, closer to this RCP 6 line, but it's still a bit early to say for sure. And just for reference, carbon greenhouse gas concentrations in the atmosphere are monitored routinely at several sites around the planet. And at the moment, the reading for the average across what's elapsed so far of May this year, we're sitting at around 417 parts per million, which is this represented roughly by this tiny dotted line, so you can see where we're sitting. This is where I got those data from, and it's interesting just to look at the way carbon dioxide concentrations in the atmosphere progress over time. This data source goes all the way back to the year 1000, but I've zoomed in on just 2000 to 2020. You can see that there's the cycle, which is a natural cycle that results, at least in part, from the breathing of the big deciduous forests in the Northern Hemisphere. They have a massive impact. But you can see that it's just gradually going up over time. There's the occasional spike, but essentially it's a fairly constant upward trend. And just briefly, because I sort of suspect some people will be wondering this, what effect has COVID-19 had on our greenhouse gas concentrations? And in this case, we're looking at emissions, not concentrations. But you can see that, you know, here's a trajectory of greenhouse gas emissions from 1970 to the present day. And right at the end here, you can see that it's plummeted very quickly. And this is a zoom in on just the period January to May this year. You can see how the emissions have dropped down, not linearly, and they've started to pick up again. Might go down again, or it might continue to go back to where it was. And in terms of where those emissions reductions have occurred, you can see that it's not evenly spread across the sectors of society. Residential emissions have actually gone up ever so slightly, but you can see surface transport, understandably, has plummeted, as has industry, and power has gone down as well. Okay, back to the main game. So we run these things called global climate models to simulate the climate of the planet. And it's not something you can do on your trusty laptop. It takes supercomputing resource like this one, which is the National Computational Infrastructure in Canberra. It's a pretty big and crunchy supercomputer, but it's nowhere near the most powerful on the planet, but it's a pretty powerful piece of gear. And if you can't afford to run a supercomputer, you can't afford to do global climate modeling. So consequently, this sort of research is mostly done by the richer nations of the world. There's over 20 research groups around the world who develop global climate models. And this is an illustration of what a global climate model looks like and how it's set up. And you can see that the little inset here is indicating the processes that the global climate models are simulating. But a really important feature of global climate models is this layering and these grid boxes. So the entire globe is divided up into cubes that are arranged in layers, and those layers go up into the atmosphere. It varies from model to model, but it's roughly 40 layers, give or take, up into the atmosphere. And in the ocean, again, it varies, but more or less 40 layers down into the ocean as well. And essentially what the supercomputers have to do is they need to solve for each of these cubes, or these grid cells, they need to solve all of the equations that they need to solve for that part of the planet simultaneously, communicate that information into the neighboring grid boxes, and then step forward in time and do it all again. And it has to do that calculation simultaneously for every grid box, step forward in time, compute them all again, step forward in time and compute them all again. Now, these equations are quite fundamental. They're from the laws of physics and chemistry, particularly energy conservation, things like that. Things that have been known for more than a century and well understood. But of course, the ability of the models to simulate the planet isn't perfect. And one of the reasons it's not perfect is just the fact that we have to divide the planet up into cubes like this, rather than be able to solve those equations in a continuous fashion in 3 dimensions. And that's because we don't yet have computers that are powerful enough to do that. So as a compromise, we have to sort of chunk the planet up into these boxes. But they do a pretty reasonable job. If I can make this play. There we go. This is an output from a global climate model, the C2SM climate model, and you can see that it is reproducing the sorts of cloud patterns that you're accustomed to seeing in satellite images, for example. And so you can zoom in and you can see that they're reproducing the processes that occur around coastlines as well as the poles. So they do a pretty good job, but they're not perfect. Beck, about to move on to the sorts of outputs that the models produce. Are there any questions that we should follow up?
No, not at the moment.
Okay, cool. No worries. Alrighty, so that's a sort of a Cook's tour of how a global climate model works, in a sense. In terms of what they produce, because of that grid pattern that you could see on the illustration before, the output comes out in a gridded form. So this is one example of a gridded temperature change output from one global climate model. And you can see that there are boxes here that represent the two-dimensional surface of that grid box that's sitting right there. And this is representing future change for the period 2080 to 2099, so roughly the end of the century. And when I say it's a change, it's important to understand how we compute that. When we compute the projected change from a global climate model, we take the 20th century simulation from that climate model, and we compare that to the 21st century simulation from the same model, and we compute an average over 20 years. And for the current set of projections, this is a period 1986 to 2005. And then depending on what future time slice we're interested in, this is illustrating the calculation for the 2070s. So that's the period 2060 to 2079. Compute the average across that 20 years and compare it to the average for the historic 20 years to come up with the calculated difference. That's important for a couple of reasons, but the main reason is that every climate model has an inherent bias. So for example, a given climate model might simulate a world that is a little bit too hot or a little bit too cold, but it does that consistently throughout its entire run. So we know that the bias in the 20th century is the same as the bias in the 21st century. So by subtracting the future value from the model, from the historic value from the same model, we're effectively removing that bias, or essentially ignoring it because it's no longer relevant. But as well as these gridded results, you can also explore the projections over time. So here's an example of a time series output, as they're called, from one model. It's this BCC model shown in purpley color here in the 21st century. The brown line in the 20th century are the observations, and in this case this is for an Australian region. So the observations come from the Bureau's high quality temperature data set called AcornSat. So you can see the historic jiggling up and down as you'd expect the annual average temperature to do. Year to year is different. And then we switch over to one version of the future as simulated by that BCC model. And you can see that it also goes up and down in much the same way as the real world observations. It doesn't capture the variability quite as well, but it is reflecting that variability. The shaded lines are a bit different. The grey shading shows the range of projected temperature from all of the global climate models from their historic runs. So in this case, there are about 30 odd models for this particular RCP. And you can see that there's a band that represents the sort of upper and lower limits of that. The dark line through the middle is the average from all of those model runs. In the future, there's a similar band, and in this case, it's computed from the future simulations from, again, the same models. And again, there's an upper and lower limit, and the mean shown in a thick line through the middle. This is a plot from the most recent national projections that came out in 2015. And if you are familiar with those reports, or if you get a chance to look at those reports, you'll see that this type of plot is produced for all the regions around Australia. But it's crucial when we're looking at climate model projections to understand that there is a range of projected change, and it's sometimes referred to as uncertainty, but it's probably more correctly referred to as just a range of change. So what this plot is showing is the global surface temperature. So this is an average temperature for the entire planet in degrees Celsius over time from 1850 through to 2300 in this case. So very often, including in the plot that we just looked at, the plots end at 2100. That's fair enough. That's, that's a pretty long time in the future. It's also the period for which we have the most data. But some of the models from the international collaboration effort are modeled right through. They let them run right through to 2300. And you can see that for each of the RCPs represented in the different colors, there's a range of change projected by the full set of the models. So for RCP 8.5, the red line, there are 39 different simulations that are used to produce this graph in that 21st century slice. So you can see that by the end of the century, there's a fairly substantial range of projected temperature change. And in this case, that projected change is relative to that time slice that I showed you earlier, 1986 to 2005 time slice. And the red line shows the median value. The median value, if you're not familiar, being the value for which half the models give a result above that value and half the models give a result below that. And if you're a bit of a stats head, this band represents the 10th to the 90th percentile values from all of those models. But you can see as we take this RCP 8.5 forward, we have quite a lot fewer models to look at. So our confidence in the range is less, but you can see that the range just keeps growing. It gets wider and wider as you go out into the future. And that's essentially true of all of the emission scenarios. The main difference being this blue line down here, which is the so-called RCP 2.6. That's an emissions, sorry, that's a concentration pathway that gives us around about a 2/3 chance of stabilizing the globe's temperature at 2 degrees by the end of the century, which would probably be aware is one of the Paris Agreement target temperatures. So very important to consider this range. We have, in effect, no way of just determining whether any one of these models is going to be right. So we have to assume that they're all plausible unless we have good reasons to reject a particular model's results. So if we choose to not consider that full range of change, then we're taking a big risk that we're not taking account of a future that is equally plausible. So that's global climate models and their results, but there's another type of modeling as well called regional climate modeling, or often referred to as downscaling. There's a couple of key approaches to doing downscaling, one of which is called dynamical downscaling, and what that really means is that it's a process that uses a model just like a global climate model, only it's being run over a smaller area, or statistical downscaling, which doesn't involve a step-by-step over time dynamical process like a climate model uses, but instead looks for statistical relationships between large-scale processes and what that might mean at a smaller scale on the ground. What we're showing here is an illustration of the sort of increase in information that you can get by downscaling. One of the key inputs to any climate model is a representation of the Earth's surface in terms of the topography. And so you can see on the left a sort of typical global climate model which has a grid box size of 150 kilometres. That's about the average size. They range from 60 to 300, but roughly they're mostly sitting around the 150 mark. And what's shown here is a representation of the topography, and you can see that it's really coarse. There's not a lot of information there. There's a bit of a difference between this region and that region, the brown being higher elevation and the green being lower elevation, but it's very chunky. The middle plot shows the topography as seen by a regional climate model, in this case a model called the CCAM model, which is a model developed by CSIRO. If that model is run at a 50 kilometre resolution, this is the way the land surface looks to that model. So you can see there's a little more definition here. The Alps are beginning to be distinguishable from the lowlands, but there's still, it's certainly better than the GCM, but it's still pretty chunky. And the plot on the right is showing the same model, but the land surface for when that model is run at 5 kilometre resolution. And you can see that now you're really starting to see peaks and valleys in the high country, and you're getting more detail even in the lowlands. But by the time you get out into the Mallee, it's really, you know, 6 of one, half a dozen of the other. There's not a lot of difference. Now, in principle, downscaling can give us more information, better information in some ways than a global climate model. But it doesn't do that everywhere. As we just saw on the previous slide, it didn't make a lot of difference to the Mallee region of Victoria. Similarly, when we look at Australia, there are regions of Australia where we expect downscaling can give us more information and new information, what's often referred to as added value. And that's where there is topography or other regional factors that are important. For example, in Northern Australia, regional modelling gives a better representation of cyclones, and so we get enhanced information there. Elsewhere in the continent, we don't expect regional climate models to add a lot of value. But even where we do expect that they have the potential to add value, you can't assume that they will. You need to, unfortunately, do the modelling, then test it. And if you're really unlucky, it won't have added much value. It often does, though. So I just mentioned evaluating the results, and that's key to developing climate change projections. So we use multiple lines of evidence when we assess climate model projections, and that helps us to determine the level of confidence that we have in a set of results. So at the most fundamental level, we're looking at global climate model results and what they say in terms of the future climate, but also what an evaluation of the results from those models tells us, and what additional insights we get from downscaling, what we know about the fundamental processes that occur in the atmosphere, and how well the projections line up with what's expected based on the trends that have been observed over the past decades. So, for example, if we have the global climate model results suggesting that there's a reduction in rainfall in a given region, and our model evaluation tells us that the results are plausible, and regional modelling gives a similar result for a reduction in rainfall, then that helps to increase our confidence that the projections are plausible. If, however, which sometimes happens, there's a disagreement, you might have global climate models saying one thing and regional climate models saying another. That might mean that the regional models have given us new information, but we need to check. So we do model evaluation, and we particularly take into account our understanding of the processes that drive the climate system. And that might tell us that, yes, by simulating at a higher resolution, we expect key processes to be better simulated, and they're behaving in the way we expect they would behave in a changing climate. So that gives us more confidence that the downscaled results are giving better information than the low resolution GCMs. But the reverse can also be true. Sometimes we get a result from high resolution modelling that we can't explain based on our process understanding. And if it disagrees with global climate models that have been shown to perform well in evaluation, that reduces our confidence in the results, particularly the results in the regional modelling. So it's quite an involved process, but it's absolutely crucial to our ability to state what the future climate might be like. In terms of the way in which we do that assessment of the model's performance, one of the most fundamental things we do is we look at how well the model has simulated the average climate over a region. In this case, we're looking at the whole planet, but you can do this same process for just Australia or anywhere else on the globe. And we compare a reconstruction of the past climate from observations with the average from all of the models when they've been run to reproduce the 20th century. And we're looking here at a period of 20 years, from 1980 to 1999. In this case, we're looking at projected change in temperature and, sorry, not projected, we're looking at the observed change in temperature and the modeled temperature, and you can see that they match up pretty well. The models are doing a really good job of simulating the temperature of the globe. They've got the spatial patterns pretty right, and the magnitudes of the change as depicted by the colors are also pretty right. But if you look closely, you'll see there are differences. And if you live there, then that's a difference that would be quite significant to you, because the models are underestimating the temperature at that spot compared to the observations from the real world. So that's one of the methods we use to evaluate the performance of global climate models. This is showing the average result from probably 24 models, but you can do this model by model, and that's what we do. We would look at every model individually, see how it compares to these observations, and give it a rating according to how well it's done that. Then we do that for other variables as well, like rainfall. But in addition to that, we also look at the trends. And one of the...
John, sorry to interrupt you.
Yeah, sure.
We just have a bunch of questions that maybe you could answer before you get too far.
Yeah, sure.
The first one is, do you only estimate a point temperature change, or also whether there is increased variability? This is in relation to the GCMs.
Okay. It's a little bit of both. The global climate models are essentially designed to simulate the mean state of the climate. So they're not so good at simulating the changes in variability, but they do show some. And you might remember back to the, well, actually we can see it here. You can see on this slide how these yellow lines, which are the output from individual models, you can see how they go up and down. It's real spaghetti, but they're going up and down in much the same way as the real world climate goes up and down. And the climate models also simulate to some extent the ways in which we would expect some of the important processes to change, like the El Nino Southern Oscillation, for example. So global climate models don't simulate ENSO perfectly, but they simulate it well enough for us to be able to detect changes in the way ENSO is expected to play out. And so that's led to findings that we expect to see intensification of El Ninos, but not so much La Ninas and things like that. So those elements of variability we can get a handle on. If we simulate with, particularly with dynamical downscaling regional models, then we get a better level of detail about that variability, at least potentially. So that's one of the big attractions of regional climate models, is the ability to simulate the variability a bit better. But essentially, most global climate model results are really talking about the mean state of the climate. So hopefully that's answered that question.
So the next, I've got 3 more. So what is the computation time and expense per modelled year?
Good question. I don't really know. The last upgrade to the national computational infrastructure, I think, costs 50 million. And to run the Australian global climate model, Access, on that to simulate 100 years takes about, well, it takes several months to run that simulation, but you do it more than once because you've got to tune the model and get it working properly. So it actually takes somewhere in the order of 5 to 7 years to get a set of global climate models to a point where people are happy to publish them. So if you take into account all of the labour goes into that, as well as the cost of the computational resources, it's a lot of money, but I couldn't put a dollar value on it. But this, I can see actually that Oliver's asked what's the time step with the modelling, which kind of relates to this as well. And no, Oliver, you didn't miss it. I didn't say it. It varies, but it could be in the order of 15 to 30 minutes generally. So you can appreciate that if you're doing a 300-year simulation, that's an awful lot of data. The regional climate models operate at a finer time step. So as well as being at finer spatial resolution, they also have shorter time steps, and it might be as short as a minute, or 10 minutes is quite common. So that's one reason why regional models can help better explore what's likely to be going on with climate variability, particularly for things like intense rainfall events, which might, you might get flash flooding from 10 minutes of intense rain, and a global climate model is just not going to see that. It will average out the rainfall over a much longer time period, and you don't get as much information, as well as the fact that it's bigger grid boxes.
Yeah. And the last one for now says, perhaps this will be covered later, but could John touch on the relationship and difference between the RCPs and the SSPs, the shares?
Right. Yeah, I deliberately left SSPs out because it's confusing. It confuses everybody, including me. Perhaps maybe we should come back to that one, I think, at the end, because it takes a bit of explaining, and I can go back to the slide with the RCPs on it and talk to that probably.
Yep.
If that's all right.
Yeah, that's it for now then.
All right, cool. Yeah, so I can see that was Dylan. So yeah, thanks. Good question. Yeah, we'll come back to it. Okie dokie. So this slide is doing a couple of things, but one of the reasons for having it there is to show you that we also evaluate climate models on how well they simulate the trends in the past. So this is a plot built up from all of the simulations that were conducted for the time period 1900 to 2020, 2010. I think from the 4th assessment report of the IPCC. And as I kind of alluded to before, the yellow spaghetti are the individual outputs from all of the models, somewhere in the order of 20-odd models. The red line is the average. So we call that an ensemble mean. So basically the ensemble being the collection of climate models, and then we compare all of the results and compute an average for every year. And that's the result of that is the red line. And the black line is a reconstruction of the global temperature from observations back to the start of the 20th century. So what this allows us to do is to compare the trends between the way the climate models have simulated the past compared to what actually happened according to the reconstructed temperature. So this is showing us that there's pretty good agreement. Obviously the real world is sort of like the equivalent of a single model output in a way, whereas the red line is the composite from from multiple models. But in terms of the trend, it matches up really quite nicely. There are periods where the Earth has gone into a warmer period that isn't reflected by all of the climate models, but you can see that there are, well, hopefully you can see, depending how good quality the video is, that there are some of the yellow traces, so the individual model results sitting up in that space. So some of the models have simulated that type of climate, even though lots of them haven't. So it gives us pretty good confidence in the ability of the models to get that sort of mean state right. Another thing that's really informative is that the black line just here has taken a real nosedive down immediately after or very soon after a major volcanic eruption. So that's the Agung volcano that's erupted, a very large eruption, put a lot of ash and other aerosols into the atmosphere, and aerosols have a cooling effect on the planet, mainly because they reflect a lot of the sun's energy back from upper parts of the atmosphere. So the planet's surface temperature goes down. Now, if global climate models can't predict volcanic eruptions, but if we tell the model that a volcano has gone off at this point and it's characterized in this way, spewed out this much sulfur dioxide, this much carbon dioxide, this much methane, whatever, then we can see how the global climate model responds to that. So if you look at the red line, you can see that it has done a similar drop to the actual observations. It's not an exact match, but you wouldn't really expect it to be. So it's done a pretty good job, and then it's resumed in much the same way that the globe's temperature resumed its upward trend. Then when we get to this point, there's another volcanic eruption, and again the temperature dips down. The climate models might have overestimated to some extent how cool it got, but nonetheless there was a drop in temperature. And again, the same thing with the Pinatubo eruption, which was obviously a pretty big one as well. So those things in combination give us pretty good confidence that the models are doing a good job. And like I said, this is also showing us that they're getting the trends, at least at global scale, right. When we zoom into smaller regions, like if we just looked at Australia, then the errors between the model simulations and the observations will get bigger. It's just a fact of the way climate models are. When you zoom in, your errors get bigger. So that's trend. And I'm going to move to the next slide now, which is another plot that has this same trace on it, just depicted slightly differently. And the reason for showing you this is that in addition to giving us information for model evaluation and assessing confidence in projections, we can also explore the causes of climate change using global climate models. And this particular plot shows one of the most powerful pieces of evidence for attributing the cause of climate change to human activities. The grey band is essentially showing the same thing as in that previous slide, the results from a whole bunch of climate model simulations with an average running mean running through it. The blue band below that is essentially the same thing, only in this case, the human-caused emissions, so greenhouse gases and aerosols, have been taken out of the equation. It's really cool because it's possible to differentiate the greenhouse gases by their source. And so it's possible to take out of the equation any that are caused by human activities, such as burning of fossil fuels. And when we do that, you can see that the global climate models are essentially giving pretty similar results. It's a smaller set of models, so it's not exactly the same. But around the middle of the century, they start to diverge. And you can see that as we get towards the present day, we're at a climate now that is significantly cooler than the real world climate. So this counterfactual climate being so much cooler tells us that the human caused emissions and aerosol concentrations in the atmosphere are what is resulting in that upward trend in temperature. So no matter what you do with these climate models, the only way you can get them to reproduce this upward trend in temperature is to include the anthropogenic greenhouse gas and aerosol emissions. Where it goes next is the topic of climate projections. So we've looked a bit about how we assess confidence in climate projections, and this is the table for the international IPCC agreed work that is a mechanism for assigning confidence statements to a specific projection. So, for example, if you look at the IPCC reports, or if you look at the Climate Change in Australia reports, you will see statements that refer to things like temperature is expected to increase throughout the 21st century with high confidence or with very high confidence. And the ways in which that's arrived at is through considering how much agreement there is in all of the different lines of evidence and what those types of evidence are in terms of the type, the quantity and the quality and the consistency. So if you've got a future projection where all of the lines of evidence agree and there's a lot of that evidence and it's all of good quality, then you will reach this sort of very high confidence corner of the matrix, high agreement and robust evidence. And at the other end of the spectrum, where you perhaps don't have very much evidence at all, and what evidence you do have is divergent in terms of what it says about the future, then we end up with this low agreement, limited evidence, which would end up in a very low confidence statement. So that's how confidence statements are derived, and it's a somewhat subjective thing. So it's often done through an expert elicitation process, where you get people who understand all of the climate factors, and you get them all sort of round a table and they nut it out together and they reach agreement. And that's how we did the confidence statements for the Climate Change in Australia projections. Okay, so we've got these things called climate projections. What can they tell us? A really important thing to understand about climate projections is that they're not predictions. Climate scientists might be the only people who draw a distinction between those two words, but we do it quite deliberately. A prediction is equivalent to a forecast. So this is the sort of thing you get from the Bureau, where you can look out several days in advance and see what the forecast says about temperature, rainfall. Rainfall is often given as a probabilistic prediction, things like that. But also, so the prediction or forecast is giving you actual values, saying it's going to be 15 degrees on Saturday with an overnight minimum of 10, but it's also giving you a particular sequence of events. And so this plot is showing a stylized prediction system where you've got the observed weather in blue, in this case it's temperature, and you've got the forecast or the prediction in red. And so you can see that there's been a forecast, and then the actual temperature that occurred on that day was slightly higher than the forecast. So the forecasters would then adjust their prediction for the following few days and then they would see what the temperature was the next day, and they would adjust the forecast again. And so you eventually, you get this system where the forecast is always pretty close to the actual weather on the day. It varies, the skill of the forecast varies, of course, and different times of year are harder to predict than others, but essentially the key point is that it's about predicting an actual value and a specific sequence of events. That's not what climate projections are about. Climate projections, as I kind of hinted at before, climate models are about simulating the mean state of the climate. And even though an individual climate model, will have its version of natural variability going on over time, it's not doing that in a predictive way. And one way to think about this is, if this was a weather forecast, then we would make the forecast, and then the next day we could check it, and then the day after that we could check it, and the day after that we could check it. With climate projections, if we're sitting here in 2020, we run a climate model and we just don't touch it again. We just have to let it go and do its thing. So there's no opportunity to stop it and to nudge it because, oh, it said it was going to be 20 degrees, but it's actually only 18. So we nudge it down a bit. There's no opportunity to do that with climate projections. So although this particular model that's being represented here in the red line is indicating a particular temperature for the year 2001, it's not a prediction that 2001 will be a cool year. It's just one of many different ways in which the climate of the future could play out on a day-to-day, month-to-month, year-to-year basis. If you took that same model and started it again, it won't follow exactly that same line. You'd expect it to give the same trend, but it won't follow that same line exactly because there's an element of chaos in the climate system, and that's reflected in the models. So I guess the take-home message from that is with projections, we're looking at the mean state of the climate, and with predictions, we're looking for an actual forecast of what it's going to be at a given point in time and how that's going to play out over time. So once we've got our models and we've evaluated them and we're happy that we've rejected any models that perform very badly and we've kept the ones that we have agreed are plausible, we can then start to look at what the results say and start to draw some conclusions about future climate. Now, this is a plot from a brochure that CSIRO and the Bureau produced called Australia's Changing Climate, I think. One of the really interesting things about these time series plots is that you can look at things like 2013 was Australia's warmest year on record at the time. That's this point here. So at the time, that was Australia's warmest year on record. It's not anymore. But if we then carry that forward in time, you can see that by sometime approaching 2040, it's down at the bottom of the range of this particular model simulation in the future. So that's under a high emissions pathway. What was the hottest year on record in 2013 becomes one of the coolest years by almost mid-century. So it's a really useful way to get people to understand what the future climate means in terms of those changes. And this plot also shows us the 2-degree global warming target and the 1.5 degree global warming target that come from the Paris Agreement in 2015. A key thing to remember before I move on from this plot is that if you read the legend, the label on this y-axis here, Australia's temperature anomalies from 1950 to 2005. So a 55-year period from here to here. But in terms of the Paris Agreement targets, you might remember that what they say is 2 degrees global warming compared to pre-industrial. So that's roughly 100 years earlier than our baseline starts. Pre-industrial period is pretty loosely defined, but we often use 1850 as a good enough estimation. So you can see that this line, the 1.5 degree global warming target, if you carry that across, it's actually slightly under 1.5. That's because there's already been some warming by the time, in the time period between 1850 and our baseline period for this plot. So that reference period is really important to understand. Climate projections are nearly always given using a much more recent historic reference period. So for the last IPCC projections report that came out in 2013, and for the last national projections that came out in 2015, we used the reference period 1986 to 2005. In the next IPCC report, due out in a year or so, that time period has been brought forward, I think 5 years. So that time period shifts. They're always trying to keep it as recent as possible, given the constraints around the modelling work. So you've got to keep that in mind. If you're looking at the projections, say, for Australia from our Climate Change in Australia reports and the data on the website, those projected changes are relative to a different baseline to the Paris Agreement target. So if you've ever looked at some results and you don't think that they make sense in terms of the Paris Agreement, that'll be why. It's that reference period. You have to take it into account. In our next set of projections, we're going to address that question specifically, so that we'll be able to show results as they relate to the pre-industrial as well as to the baseline, which will be something like 1990 to 2010. So we're developing some new projections and analysing existing projections for the electricity sector. And as part of the work, we're developing a risk assessment framework that is intended to be appropriate for the sector. And this is the current version of it. We've been talking about climate projections, and that's where they fit in. Step 2, assessing the impact and identifying the risk. So we need to know what the future climate's going to be so that we can work out what impact that will have and therefore identify the risk, and before we can start to think about how we might deal with that. So that's the context for the projections work. And just to give you an example of the sort of thing that we're developing, as part of the ESCI project, we're doing a series of case studies, and the first one of those is in an advanced draft stage. You can actually get a copy of it. You'll soon be able to get a copy of the current draft. And what we've done for that is we've developed up projected future temperatures in terms of the 1 in 10 year maximum temperature, which was particularly relevant to the wind farm output. So produce these spatial plots showing the 1 in 10 year maximum temperature and see how that changes into the future, and then assess what that means. So in the context of a wind farm near Adelaide with an historic projected 10% POE temperature of 44 degrees. Sorry, I don't understand that. Somebody want to jump in and fill me in on that?
Yeah, sorry, John, it's Judith here. Because it's my slide and I think I made a typo. So it was, I think I missed a piece of information, that was all. So what we looked at was historically 1961 to 2020, the projected 10% POE probability of exceedance was 44 degree temperature, but in the future that will, a 1 in 10 year high temperature would change to 46 degrees. So it doesn't look like a big difference, but if you look at the temperature traces on the left-hand side, you'll see that it means the output on a very hot day. Each of those lines on the left-hand side is an output as a function of temperature. So on a very hot day, it drops from an output of 40% of peak capacity on a 44 degree day to 0% of peak capacity on a 46 degree day, which has an impact on the business case, but also on whether the whole system can produce enough electricity on a high demand day. Back to you, John.
Thanks, Judith. Saved my bacon. So we can use the climate projections to develop these high resolution maps of future temperature, which then get input to the impact assessment, as Judith has just explained. Thanks, Judith. So I was just going to finish up with, which is essentially what Judith has just said, I think. We're looking at the, through that process, looking at the investment risk and possible adaptation solutions, things like more robust specifications for infrastructure and so on. And just as another snapshot of the ways in which we can use climate projections to develop additional information that's relevant to the sector, there's very robust evidence that fire weather has become more dangerous since the mid-1900s. We know that fire seasons have become longer and they're starting earlier, and the projections tell us that those trends are expected to continue into the future. And so you can dig into the detail of these high resolution fire weather projections, which were developed by the Bureau of Meteorology, and explore for given locations what that might mean. So for example, Bendigo, the number of dangerous fire days, which is defined as days where the forest fire danger index is goes above the historic 95th percentile. So those days are expected to increase by a median of 11.4 days per year by the middle of the century under high emissions. So there are multiple simulations of this, and so the median value from all of those simulations comes out 11.2 days per year. That represents a 62% increase in the number of dangerous fire days. So we know that fire impacts on particularly electricity distribution, but also poses a risk to infrastructure as well. So it's an important thing for us to have some understanding of. And in fact, the next case study that we're working on is around bushfires for that very reason. That particular set of results, though, came from some work we did for Victoria. And if you're interested in looking at that in any more detail, there's a URL for that down there. And the projections themselves were done, as I mentioned, by the Bureau as part of the National Environmental Science Program research that was done by Andrew Dowdy at the Bureau. And I'm going to leave it there.
Thanks, John. There was just a couple of questions.
Yeah.
So
should we go back to the SSP's question first, do you think?
So I think we'll go back to the SSP's question. Do you have it in front of you, or do you want me to find it?
That's right, got it. The question, I think, is what's the difference between and the relationship between RCPs and SSPs? So the RCPs, which stands for Representative Concentration Pathway, these were defined first back in 2011, and it was always the intention that there would be an additional layer of information added onto those around socioeconomic scenarios. That's what the SSPs are, shared socioeconomic pathways. and there's a relationship between them insofar as some RCPs can only be achieved under certain SSPs, and some RCPs could be achieved under multiple socioeconomic pathways. So in other words, there are different ways to get to the same endpoint, depending on the way in which economies are structured, the way in which trade is occurring, what happens to population, what happens to population distribution, and all of those different factors. So a good example might be, it's possible to get greenhouse gas concentrations, say to here, by taking a path that would actually see the concentrations go up and then back down again. And conversely, to achieve that pathway, it's possible for emissions to follow a different trajectory to this one. That's probably just confusing everybody. I might stop there because I don't have a slide handy that shows it any better. I think the take home is it kind of defines how we get there. The RCP shows us where we get to, and the SSPs are different ways that we might get to that point in terms of the socioeconomic factors. Dylan, jump in if that's not answered your question properly in the chat or however you like.
Okay. That's all good.
Oh, Dylan's happy. Yay.
So the next one is, you emphasize that the modelling focuses on long-term means. I assume that insurance companies are very interested in both climate models and the distribution of outcomes. Do you know what approaches insurance companies take to climate modelling? I ask because we'd also be interested in the results in the form of probability distributions.
Insurance companies, well, how to answer that? Start by saying that insurance companies were one of the first to get moving in terms of assessing the expected impacts of the changing climate, particularly the reinsurers, the ones who insure the insurance companies. They've been very active, and they do a lot of asset mapping and then applying the ranges of change in the future climate to those assets. I don't remember though if they're using a particular probability threshold or not. Some are using a scenarios approach where you say, look at projected changes in temperature and rainfall, and you say, well, what would a hot dry climate mean? What would a less hot wet climate mean? And explore the impacts that way. But yeah, I'm not really able to answer it any more than that, other than to say that they keep their cards pretty close to their chest, so it's not always possible to get at their methods. But having said that, there is a lot of work happening in Australia and globally, at least in part as a consequence of the TCFD, the Task Force on Climate-Related Disclosures, that is requiring companies to report their risk associated with exposure to the changing climate, and the insurance industry is very active in that space. I can probably put you in touch with somebody who can give you a better answer. So whoever asked that question, if you want to, drop us your email address and put you in touch with some others.
And One more question, which was in relation to wind generation output in relation to temperature. It says, what data sets will be available based on this modelling that will enable us to create similar analysis for wind and solar?
Sorry, I'm just reading Judith's post to the chat. Judith, would you like to talk to that question from Joseph about the wind generation data sets?
Yeah, sure. So, Joseph, we've done that as a case study, and the traces that you saw, which were using the modeling, which modeled the wind farm output. Actually, let me just back up a second. Solar response to temperature is very well understood. It's based on the physics, and the specification is quite easy to model. So then what you would need would be the underlying climate data set. We don't have final versions of that yet, but that will be an output of the project. The wind farm modeling was quite a lot more complicated because it depends much more on the engineering and the choice that the wind farm developer has made on the specs of the farm itself. So the traces that you see there on the slide that John's just put up are based on AEMO modeling of the output of wind farms. When we talk to wind farm developers, they would probably do their own version of that modeling, but once again, the project is intending to make those, the underlying climate change, or the time series of how the variables are changing, to make those available. What you will see, as John said, hopefully in the next week, is a much more detailed write-up of this case study, which we will make available in draft form on the ESCI webpage. And as I said in the chat there, we're working with the electricity sector to ask them whether they want the information in time series form or in map form, but we hope to make it available. Does that answer your question, or is that, or did you want to ask something else? Okay, thanks.
Cool. And do you want to speak to what you've just written in the chat?
Sure. I was just, your question, Oliver, on probability ranges was specifically about insurance, but it did make me reflect on the needs, again, of the electricity sector. So this presentation was a very excellent presentation from John. Went through some of the basic climate information, but we are actively working with the sector to understand in what form they want the data to be available. What would be most useful? Probability ranges are an option, but come with an awful lot of their own. John's a climate scientist, so he can explain why that could be very complicated. But certainly what we're working with the sector on is how to communicate the uncertain, or the ranges, the uncertainty, whether it's a confidence narrative, or whether they actually do want the full range, whether they want the probability density function that goes along with it. And so to try and understand if it's going into the market models and guiding investment decisions, what is the information that's most useful?
It might be worth just commenting on probabilities. It's it's used in multiple ways in the climate impact space, because there's we give probabilistic climate projections very often, and they're the sort that we've been talking about, where we'll say, it's going to get 2 degrees hotter, but with a range of between 1.5 and 2.6, and that's a probabilistic projection based purely on the statistics of all of the data that we have at hand. But we're not really able to say from that, oh, this particular model says it's going to get to 1.4 degrees. We can't say that that is a X% probability of happening, partly because to do that, you have to assume that every climate model result is equally likely, and we know that's well, they're equally plausible, but they're not independent. So sorry, we need to know that the individual data points in such a distribution are truly independent to make meaningful probabilistic statements about how likely a particular future is to come to pass. But the climate models are not independent of each other, mainly because they are so incredibly complex. To build one from scratch would take multiple people's lifetimes. So we actually, most modelling groups take parts of existing models and put them together in new ways, or might build a new module and bolt that onto other modules that they've got from other research groups, or even from old versions of models from their own research group. But as a consequence, there's a lot of sharing of computer code, and you can actually do up a taxonomy of climate models and look at how interrelated they are. And our colleague Leanne Webb did that for the climate change in Australia projections work as part of the process of identifying a subset of models that we would recommend for use in impact assessment for Australia. And one of the steps in that process was to choose the models that were as independent as possible from each other. So it's pretty complicated, and because it takes so long to do these simulations, it's not possible to do tens of thousands of simulations like you would if you took a Monte Carlo style approach. That would be fantastic if we could do it, and maybe one day in the future we'll have quantum computers and that'll let us do thousands and thousands of simulations. But until we get there, those future probabilities are really quite difficult, and there's a lot of caveats around them when they are given. I don't know if that makes sense. Hope so.
Okay, so since I can't see any further questions, I guess that brings us to the end of the webinar. I'd like to thank John for presenting such an informative webinar today, and also to everyone who's attended for your time and your interest in the project and all of your questions. A recording of today's webinar will be available shortly. We would appreciate it if you could take the time to fill in a short 2-minute survey on today's webinar. The link's in the chat. Your input will be extremely valuable to ensure that these webinars are relevant for you. If you have any questions about today's webinar or the ESCI project, please don't hesitate to contact us. Make sure you look out for the next ESCI webinar, the details of which will be distributed shortly. And thanks again for attending, and we look forward to seeing you at the next project webinar. Thanks.
Thanks, everybody. Bye.